Yesterday I recorded a quick video in which I showed how you can use superposition to analyse circuits where there was more than one power supply to calculate the current through and potential difference across each component. And at the end of that video I said that you couldn't use the principle of superposition in circuits where there are diodes. Well, this morning while I was in the shower I was thinking about this and I realised that that's not actually true. Well, not if we use ideal diodes. So let me show you what I mean. Let's just switch this over. There we go. Here's a circuit with 3 resistors and a diode, and it's quite a complicated circuit. If we wanted to know the current through and potential difference across each one of these components, well, what we'd have to do if we're using simultaneous equations is go through the same process I demonstrated in the last video, which I'll show you quite quickly now. Starting from the very beginning, from the very top here, we've got Kirchhoff's first law, and the notation I've used here, same notation I used in the previous video. If you've not watched that, go and watch it, it's worth watching. But the notation I've used here is the current through the 100 ohm resistor, I'm calling I100, through the 50 ohm resistor, I'm calling that I50, through the 20 ohm resistor, I'm calling that I20. Bear in mind the current through the 100 ohm resistor will be the same as the current through the 6 volt power supply, and the current through the 20 ohm resistor will be the same as the current through the diode. In this notation, V100 is the potential difference across the 100 ohm resistor, V50 is the potential difference across the 50 ohm resistor, V20 is the potential difference across the 20 ohm resistor, and I'm assuming the potential difference across the diode is 0.7 volts. It's not bad. For a silicon diode, that's pretty much what you get when you do the characteristics of the diode and you get that knee in the graph. It's around about 0.7 volts is reasonable. So, Kirchhoff's first law here. In this branch, we have 100 ohms coming in here, then it splits in 2 directions. And where there's the split, 50 ohms goes down, I50 goes down, I20 goes across, so I50 plus I20 must equal I100. Kirchhoff, or sometimes it's pronounced Kirchhoff, but I can't do that. So Kirchhoff's first law. Kirchhoff's second, let's label it. Let's label that Kirchhoff's first law. Now these two come from Kirchhoff's second law. Kirchhoff's second law is Kirchhoff's voltage law for loops. So if we look at each of these loops in turn, the first loop, we pick up 6 volts, then we drop off V100, drop off V50, and then we're back to the power supply, and that's the loop. The second loop we're going to look at is picking up 6 volts, then we're going to drop off V20, then drop off 0.7, and then we're back at the power supply again. So you can see we've got those 2 different loops that we are going to analyse. I might as well leave that coloured in. And let's actually highlight the equations that correspond to each of these loops, because that might make it more helpful for someone to understand what's going on later on. So we're going to use our definition of resistance, V equals IR here. V equals I R. So the resistance of the 100 ohm resistor is 100 ohms, the current through it is I100, and so V100 must equal this. We can do the same thing with the 50 ohm resistor, same thing with the 20 ohm resistor. And then what we can do is, well, I mean, this actually is it. These are the 1, 2, 3, 4, 5, 6 simultaneous equations we're going to look at with 6 unknowns. I20, I50, I100, V20, V50, V100. That's a lot of equations. So let's start putting these together. If we substitute into this yellow equation the V100 and the V50, we get this. If we substitute into the blue equation the V100 and the V20, we get this. And hopefully you can see how that works. This bit here is just this bit here to replace this bit here, and so on and so on. So that's sort of, basic algebra stuff. Now if we scroll down to the next part, we've got our 2 equations at the top there. Let's leave them there. Those are the 2 equations that we were left with before. I'm going to take each of these and rearrange it. because I'm going to substitute these two equations into that first equation for Kirchhoff's first law. The first equation for Kirchhoff's first law was I100 equals I50 plus I20. So I want to get rid of the I50 and get rid of the I20 and replace them with things in terms of I100. And that's what we've got here. If I take the first equation here, that's the same as this equation here. Now I take the second equation here, that's the same as the second equation here, except they've been rearranged. So if I use my colour coding, this was the yellow equation, this is the yellow equation here, this was the turquoise equation or blue equation, and this is the turquoise or blue equation there. So you can see all I've done is rearrange the equations. Let's get rid of those colours so we can see the equations a bit clearer. I've rearranged the equations to leave the I100 and make the other variable the subject. Now I can substitute those into our Kirchhoff's first law equation. I100 was equal to I50. Well, this was I50 plus I20. Well, this was I20, all this mess here. Now, I've done a few steps here to make it a little bit simpler for me. So I've done 6 divided by 50, subtract 100 divided by 50 times I100. So I kind of split this fraction. And 100 divided by 50 is just 2, which is why I wrote 2 times I100 there. So I'm hoping you can see, again, using our colour coding, if this is the yellow equation here, then this is the yellow equation cropping up there. And I've done the same thing where I've split the fraction, 6 over 20, 6 over 20. 100 over 20 is the same as 5. And I've left the 0.7 over 20 there. So this is the blue equation, and this part here is the blue equation. So I'm hoping you can see how that follows through. Right, so we're now here. Scrolled up. We've only got one unknown, which is I100. So we can rearrange that to make I100 the subject really easily, actually, because we've got I100, and on the other side, subtract 2 I100, so we can add 2 I100 to both sides, and subtract 5 I100, so we can add 5 I100 to both sides. So 1 I100 plus 2 I100 plus 5 I100 is 8 I100. Fine. And the rest of it is all just numbers. Here I just did the 6 subtract 0.7 and put it back together into the same fraction to save a little bit of space. But that's easy algebra, that's easy arithmetic to do. Divide by 8, because I've divided both sides by 8, and you get 48.1 milliamps. Also, it says 41.8 milliamps. Well, let's just check and see if that's what our little circuit simulation says I100 should be. So I100, let's just turn animations on. I100, we reckon it's 48.1 milliamps. It is 48.1 milliamps. So that works. And once you've got one of these, you can solve it for all of the rest. Once you've got one of these values. So let's just turn that off for a second. Now we've got I100. It's pretty straightforward. We're just going to use V equals IR over and over and over again. So the potential difference across the 100 ohm resistor is just going to be the current multiplied by its resistance, which is 4.81 volts. Once you've got that, we can use Kirchhoff's second law to calculate what the potential difference is across the 50 ohm resistor. We picked up 6 volts, we subtract 4.81 volts, and what we're left with is 1.19 volts. Once you've got 1.19 volts here, I50, this is the bottom line of algebra on the screen, is just going to be the potential difference divided by the resistance. So that's 23.8 milliamps. So now we've got the current through this one here and the current through this one here. We can use Kirchhoff's first law to determine the current through there. I'm just going to label these. So 48.1 milliamps. I always put the milliamps when I'm working in some some prefix, some unit prefix. Rather than writing standard form or writing 0.0481, I'm writing it as milliamps. So this is 23.8 23.8 milliamps. And so what are we left with here? Well, that's just going to be 48.1, subtract 23.8, which is exactly what I do next. Now, just be careful with this. I've got a little bit of a round-off error. I've rounded these numbers, you see. And because I've rounded these numbers when I've written them down, if you write into your calculator exactly what I've written down, you won't get this answer. This answer comes from when I use unrounded numbers. So just be a little bit careful of that. Really, I've done this wrong. I should here have written the answer with the round-off error. I've just made a note here that there will be a round-off error, but I've used what was in my calculator already, which is why when you type this into your calculator, you don't get this. But if you follow through the maths yourself and don't round anything, then you will get this. So I'm sticking with this to get the most accurate answer I can. So now you've got your 24.4 milliamps through that part there. You can just about see that smudge of a number, doesn't matter. V20, easy, that's just I times R. We now know I is 24.4 milliamps times by R, which is 20, gives you 0.488 volts. And let's just double check. If this is 0.7 volts and we add it to 0.488 volts, we should get the same potential difference as we've got across the 50 ohm resistor, and we do. So we now know the potential difference across and current through every component in this circuit. It took a bit of work, that's the problem. I mean, this has been recording for over 10 minutes, 11 minutes now. 11 minutes of this, which I wrote down in advance. If I was writing this in real time, it would take perhaps a bit longer. So there must be a quicker way. Well, it turns out that we can use superposition. And it is, I think, a little bit easier. So let's just take our circuit, and like we did last time, and if you don't know what I'm talking about when I talk about superposition, watch the last video. We're going to replace this diode with a power supply. Now, the reason we can do this is because we're treating this diode as being a sink of 0.7 volts. So it's effectively a perfect power supply with zero internal resistance of 0.7 volts, but with a polarity with the positive this side and the negative this side. It would do the same job. Let me show you what I mean. I've taken that circuit and I've split it into the top one. So I've just replaced that diode, which we're pretending is a power supply. I've replaced that with a wire. And then I replaced the power supply, the 6 volt, with a wire, and the diode with a power supply in the opposite direction. Okay, that's our 0.7 volt sink right there. Now, these two circuits are going to be easier to analyse. If I zoom out so you can see, hopefully, all three circuits together. Not sure how clear that is. The first one is just take off the diode, replace it with the wire. The second one is take off the power supply, but replace the diode with a power supply in the opposite direction. That's what it's doing. It's taking away 0.7 volts. So any current passing down through this power supply is going to cause a reduction of potential of 0.7 volts. That's the same thing as a power supply in the opposite direction. It's a bit of a faff, but as long as you can look at that and think, yeah, okay, that kind of makes sense, and visualize it in terms of potentials, it does actually work. And if you're not sure how to visualize potential drops across circuits, then I did a video some time ago, some weeks ago now, where I got the Gravitrax out and tried to show you how you can use height to visualize gravitational potential and then link that to electric potential. So you've got a model you can use to visualize what's going on. Right, let's use superposition. I started 15 minutes ago saying that you could use superposition. Let's use superposition and see if it's easier than simultaneous equations. So here are our two circuits. Starting with the top circuit, the combined resistance is just going to be 100 ohms plus. Now careful, because these are in parallel with each other. So the resistance is the reciprocal of the sum of the reciprocals. So 50 ohms. Take the reciprocal plus 20 ohm, no, take the reciprocal, and then take the reciprocal of both of those. So the resistance of this network between this point and this point is 114.3 ohms. And there's 6 volts between this point and this point. So the current through the power supply is 52.5 milliamps. Well, that's the same thing. That is the current through the 100 ohm resistor, because that's the same current as goes through the power supply. So that's fine. We've got that current. Now let's look at the second case. So in the second case, the second of our 2 circuits, what I did is I replaced the diode with a power supply, thought of it as a power supply, and I replaced the power supply with just a wire. And here the combined resistance is 20 ohms plus these 2 in parallel, so that's the reciprocal of the sum of their reciprocals. So you get 53.33. There's a recurring dot on that, but we don't use recurring dots in physics. Fine, whatever, you've got that. Calculate the current through the 20 ohm resistor. So that's going to be 0.7 volts divided by the resistance of the network between this point and this point, which we've already decided is 53.33 ohms. And that gives you the current through the power supply is 13.13, near enough, rounded there, 13.13 milliamperes, which is going to be the same as the current through the 20 ohm resistor, which is why I've labelled it I20. So what's I100? Well, this is a current divider, and I looked at current dividers when I did superposition in the last video as well. So I'm not going to go into too much about how this works, but it's quite straightforward to work out. If you know the current through this part here, 13.13 milliamps, then you know there's going to be half as much current through this branch as there is through this branch. In other words, of the total current, this one is going to get 1/3 and this one is going to get 2/3 of the total current, because this one's got twice the resistance of this, it gets half the current of this, so there we go. So the easy way to work that out is to do the resistance of the branch you're not using divided by the total resistance. And that's the same thing as 1/3. So there we go. We've got to have 13.13 milliamps multiplied by third gives you 4.375. Now again, if you do the maths on this, you don't get that number if you use my rounded numbers. This is using unrounded numbers. You will get a round off error and write down a different number if you're using rounded numbers. Okay, fine, so what? Well, let's just have a look at the 100 ohm resistor. So a reminder of the circuit, the 100 ohm resistor, scroll right the way to the top, can't easily see it. Where's the 100 ohm resistor? These both like this. The 100 ohm resistor here, the 100 ohm resistor here. Now the 100 ohm resistor here, the current is flowing through it in this direction. The 100 ohm resistor here, the current's flowing through it in the opposite direction. So you've got to be careful here. We've calculated, oh, there's the circuit. Anyway, we've calculated the current through the 100 ohm resistor, but in 2 directions. Now, what do we mean by current direction? Because current is a scalar. Well, leave that for now. It's a colloquial way of talking that makes it slightly easier to communicate with each other, so we'll stick with it, and we can have a big, long discussion. Get in the comments of this video, discuss, is current a vector or a scalar? It's a scalar! But it's a bit of a mouthful to talk about the direction of the average drift velocity of effective positive charges or something like that. It's a bit of a mouthful. Anyway, 52.5 milliamps going this way, but 4.375 milliamps going the other way. So what is I100? Actually, in our combined circuit, the superposition, which just means adding together, that's all superposition means. So we're going to add together those 2 currents to get 48.1 milliamps. Oh, that sounds familiar. 48.1 milliamps. I think that's exactly what we got for I100 when we used superposition. 48.1 milliamps. There it is. Not when we used superposition, sorry. When we used simultaneous equations. That's the point. When we did simultaneous equations, it took us ages to get to this point. But if we use superposition, it's going to be much quicker to get the 48.1 milliamps. And once you've got one value in this circuit, you can work out the rest. And it's really quick to do. You can rattle through these really quickly. Once we've got the I100 is 48.1 milliamps, Then V100 is just going to be V equals IR, so times that current by its resistance, by that resistor's resistance, you get 4.81 volts, which is the same as we had before. And then that's going to be 6 subtract this, so Kirchhoff's second law on this loop here. So 6 subtract 4.81 gives you 1.19 volts, exactly what we had before. So then we know the current through this particular resistor here is going to be V divided by R, which is 23.8 milliamps, exactly what we had before. So then the current through this one, using Kirchhoff's first law, is going to be the current through the 100 ohm resistor, subtract the current through the 50 ohm resistor. So what's left is the current through the 20 ohm resistor. 24.4 milliamps again. There's our round off error, but that's exactly what we got before. And now we know what the current is through this resistor, just multiply it by its resistance to get the potential difference across it. 0.488 volts, which is exactly what we had before. So you can use superposition with diodes, turns out, but you've got to treat the diode as a power supply in the opposite direction with 0.7 volts. And that's all I have to say about that. Hopefully that's useful.